Today, we're going to start talking about circular momentum. So, one of the first things we need to do is when we're talking about movement in two dimensions, one dimension, well, I guess not one dimension, but two dimensions, when we're talking about being like north of south or, degrees from the horizontal, we really like talking about angles and degrees. It was nice, easy, allows our trig to work really, really well. However, when we're talking about circular motion, we're talking about changes in movement around a center point of rotation or revolution, we're going to need to go ahead and change from degrees to radians. This simply is just an easier way to kind of think about movement in a circle. So kind of if you need a refresher on how radians work, really when we're looking at like a circle, one full circle, one full rotation, we think of it as 360 degrees. That's really 2 pi radians. So if a full circle is 2 pi radians, then 180 degrees or half a circle would be just pi radians. And then we can kind of break it up a little bit from there. For instance, 45 degrees is a quarter of half a circle. So that's pi over 4 radians, stuff like that. Typically, for physicists and engineers, they consider uh, movement, rotation in a clockwise motion. So this way to be considered negative, uh, a change in angle. Uh, Counterclockwise would be a positive change in angle. Yeah. So we're going to have two formulas we're going to use just kind of starting off. The first is this kind of weird, funny looking W here. It's a Greek letter. It stands for angular velocity. We can either think of it as radians per second. A lot of the times you're going to see it as like 1 over seconds or seconds raised to the minus 1 power. To find angular velocity, really all we're going to do is we're going to take our change in angular position, our change in angle, and divide it by time. That's just like how we did regular, plain old, everyday velocity, was we just took change in distance divided by time. But in this case, since we're curious how an angle changes, change in angle over time. The other, and time, once again, we're looking at seconds. The other thing we can look at is we can look at tangential speed. If you've ever been on a merry-go-round, you know that you can have either a little bit of speed, if you're towards the middle of the merry-go-round, or you could have a lot of speed if you're towards the outside of it. And really, to find tangential speed, what you're going to do, so tangential speed is just meters per second. To briefly explain what a tangent is let's say, well, that's not a bad circle actually. So let's say that we're rotating this way. We know that, like, let's say it's a ball on a string. Really, we know as we're spinning it around, in this case, that would be in the clockwise motion, so that's negative. We know that if we let it go right here, what the tangent is, a tangent, in geometry is just a line that only touches a circle at one point. What my tangential speed, though, is going to be is kind of a, if I let it go, how fast will it be going is essentially what that kind of tangential speed really tells us. So with all that in mind, let's look at some practice problems here. All right, so first one we got here, down there at the bottom. An antique long-playing phonograph or an LP record rotates clockwise at 33 and a third revolutions per minute, so RPMs. What is its angular velocity per second? All right, so in this case, we have, first off, it's moving clockwise, so we know our RPMs really should be kind of negative. So let's call that negative 33 and a third. Let's see, RPMs, revolutions per minute. So we're going to go with revolutions per minute. This one's going to have a little bit more work than typically what I'd ask of you. All right, so first thing we need to do is we need to figure out revolutions per minute. Well, let's figure out how many revolutions per second there is. So let's go with 1 minute on top. And in 1 minute, there are 60 seconds, okay? Minutes cancels minutes, okay? So we're good so far. So now I'm at revolutions per second. But in order to use this, I need to know angle. So rather than talking about revolutions, I know one revolution is 2 pi. So let's go with there are 2 pi radians. Let's pretend that says radians in 1 revolution. All right, so in this case, revolutions cancels revolutions. So I'm going to take negative 33 and a third, or negative 33.3, divided by 60, and take that times 2 pi. All right, so bring this guy over. Let's see, so we got 33.3 negative. We said that was divided by 60 times 2 pi equals not the right answer. All right, let's try that. 33.3 negative divided by 60 times 2. Let's go times pi. Negative. That gets us the right answer. So in this case, that'll be equal to negative 3.49. So, wow, okay. Negative 3.49. And once again, I would say just go with radians per second. Just kind of keep it easy. So an LP record, that's kind of their angular momentum. And once again, it's negative because they move in the clockwise motion. All right, so let's look at one that's maybe a little bit tougher. Let's go there. All right, so merry-go-rounds. Let's say that there we go. Merry-go-round. All right, computer is possessed, evidently. Okay, a merry-go-round takes 7.5 seconds to complete 1 revolution. If your place on the merry-go-round is 4.3 meters from the center, what is your tangential speed? All right, so in this case, if I wanted to kind of diagram this out, let's say that I'm even on the outside of the merry-go-round. Okay, that's the center of the merry-go-round. That's where I'm at, and let's say that that distance is 4.3 meters. Okay, that's my radius. My radius is 4.3 meters. That's how far away from the middle I am. And I want to know what's my tangential speed if the merry-go-round takes 7.5 seconds to essentially go from here to go all the way around. So it'll be my t. And in this case, my change in angle that they gave me, 1 revolution for 1 circle once again, make it a complete circle. That's 2 pi radians. All right, let's write that so it's actually kind of legible here. Okay, so we got t is equal to 7.5 seconds. That's how long it takes to undergo 1 revolution, or 2 pi radians. I know that the radius, how far away I am from the middle, is 4.3 meters. All right, so the first thing we need to do is we need to figure out angular momentum. So in this case, angular momentum is equal to the change in angle, so 2 pi radians, over the time, which is 7.5 seconds. Okay, so bring our calculator back over. We've got 2 times pi divided by 7.5. So for that, our angular momentum is roughly 0.84 radians per second. All right, so now I need to figure out what my tangential velocity is. So in this case, I'm going to take my radius, 4.3 meters. I'm going to take that times our angular velocity, which is, we figured out, was 0.84 radians per second. All right, so calculator time. So we'll just take that, leave that there, times 4.3. 3.6 is what we get. So we got a tangential velocity at 3.6 meters per second. Let's see, does it mention which way I guess in this case it's tangential speed, not necessarily tangential velocity. So the positive and negative we can kind of forget about, with the way I drew it, we would have negative, but tangential speed, not velocity, so direction doesn't really matter for this one. One of the things we should intuitively see is it shouldn't matter what our tangential speed is, but the farther away from the middle we go, the faster our tangential speed should be. Like, let's say that I have a 1 meter tall wooden board that falls to the ground, okay, compared to a 3 meter tall board that needs to fall to the ground. If they fall with the exact same angular momentum, they cover this um, pi over 2 radians in the exact same amount of time. The end of this 1 meter board is going to move a lot slower than the end of the 3 meter board, okay? Because the ends are both going to hit at the exact same time. But if our change in velocity is the same, our radius is going to drastically increase our, our tangential speed. Another place where we see this is marching band folks. You're going to have a kind of a head start on this. You know that when you're marching in formation, street marching, and you go to turn a corner, the people on the inside of the turn go a lot slower than the people on the outside. And really, that's because in order to keep that line straight and keep your angular velocity the same, the people on the outside have to go faster than the people on the inside. And that still comes back to this stuff. I know it's just kind of a here's some angular velocity momentum stuff, not momentum, um, but I think it does give us a good practice with using radians as well. So with that, good luck with the practice and have fun.